In the first section of this chapter, we talked about finding the integral or the antiderivative function. And in the second section, we seem to talk about an unrelated idea, the area under a curve, or between the graph of a function, the x-axis, and within an interval. Now, in this section, we're going to bring the two ideas together with a definition. The definition, however, is a rather general definition, and it involves a sum that's referred to as a Riemann sum. Now, we have been, when we were dealing with those sums in the last section, in order to add the rectangles to find the area, those were Riemann sums, but they were a little more specific than the Riemann sum definition. Let's extend what we talked about in the last section just a little bit, and then I'll tell you about the Riemann sum idea. This sum is a Riemann sum, but it's a rather special case of it because of the delta x here. Remember, delta x was the width of each of the rectangles we were talking about, and the delta x value was the same for every one of those rectangles, and that restriction is just unnecessary. Incidentally, the delta x was figured as b minus a over n. Recall that this f of c subscript I is, we can think of it as a horizontal distance that falls in the ith interval, you see. And it doesn't matter where that value falls in the ith interval. And we've already talked about that idea that, gee, we make that horizontal distance fall on the left shoulder of the rectangle or the right shoulder of the rectangle, but it could fall anywhere within the width of the rectangle or within the interval if we're talking about it in those kinds of terms. All right, but at any rate, this is a Riemann sum, but it's rather restricted. Let's expand the idea by doing this, by making a definition. Let's say that this is the notation for the length of the largest subinterval within the interval a to b. Now, by subinterval, I'm talking about the widths of rectangles. The length of the largest subinterval would correspond with width of rectangles, and we're saying that those widths need not be identical with one another. And if they're not identical, let's just say that this is the symbol for the length of the largest one, or the widest rectangle within this interval. Now, let's call that by a name. Let's say that this stands for what we'll call the norm of that interval. Okay, so the widest one, the widest interval, the largest width of a rectangle is called the norm of the interval a to b. Now, if it may turn out that we structure the situation so that all of those rectangles have the same width. And if those subintervals are all of equal length, that is, they're all the same as we have had before, they're all delta x's, then the partition, the separation within the interval a to b is said to be regular. So the partition is regular, and the norm is really just delta x, which is calculated as b minus a over n. So this idea of the norm just allows us to expand this definition for summation just a little bit. Well, let's understand that if we're talking about and let's keep it on the basis of widths of rectangles for the time being because it's easy to imagine, but if those widths of rectangles are of differing amounts, that is, the widths are different from one another, and the norm is the largest of all of those, imagine what happens as the norm gets smaller and smaller. Doesn't that imply that, gee, if we have a to b, you see, if we have this overall interval, and we have a bunch of rectangles in here, and they have widths associated with them, then in order for the largest width to approach 0, the number of rectangles has to approach infinity. And that's kind of an important idea to tie in with what we have been talking about. That is, as the norm approaches 0, the width of the widest rectangle approaches 0, that implies that the number of rectangles is approaching infinity. All right, now we're ready for a definition. The definition will contain a Riemann sum, a rather general summation definition, and I'll point it out to you when we get to it. This is the marriage of the idea of integral and integration with the idea of area from the previous section. Okay, we're going to define this way. F is defined on the interval a to b, and the limit below exists. Okay, that sets us up. The limit as the norm approaches 0. Now, this implies the same thing. This implies that n is approaching infinity. So we just as well say the limit as n approaches infinity, but this is a general way of beginning the whole idea. Now here's the Riemann sum. The sum as I runs from 1 to n of f of c sub I of delta x subscript I. Now this is a general width, you see, of one of those rectangles. I'll describe it a little more down below, but this is equal to the integral from a to b of f of x dx. Now, when we talked about integral in the first section of this chapter, we were talking about an integral function. This is not an integral function. This is a definite integral. It's the integral within an interval. All right? And we'll have a lot more to say about that, but this is quite a bit different from what we were talking about. It's related, it's a cousin, but it's not the same thing that we were talking about in the first section of this chapter. Okay, the a here is the lower limit of integration. The b is called the upper limit of integration. And the a and the b correspond now with the interval that we were talking about to begin with here. And c subscript I is any point on the ith subinterval, and we've already talked about that quite a bit. The delta x subscript I, delta x sub I, is the width of the ith subinterval. And notice that it isn't restricted to a particular value. Now we will restrict the delta x sub I. We will make those widths of rectangles all consistent for computational purposes. And as a matter of fact, we're going to designate where the c subscript I and the c sub I falls on each interval for computational purposes. But the more general form of the situation is this, and that gives us our definition for definite integral. Okay, it's important for us to establish now and understand that a definite integral that we're just defining here is a number. And that number can be positive, it can be negative, or it can be 0. Now it seems like we are relating the idea to an area between the graph of a function and the x-axis and within an interval, and we are. That's one application of the situation, but the situation is more expansive than that. You know, if we're just talking about that kind of application, then the value would always be positive. But the value doesn't always need to be positive, so we need not always think of it in terms of area. We can at the moment, however. Okay, so a definite integral is a number. An indefinite integral is a family of functions, and this is what we were doing in the first section of this chapter. All right, let's find a definite integral. Let's actually make the calculation here, and we make the calculation according to this limit idea. Now, there are going to be some shortcuts here, and I'll show you the shortcuts later, but for the time being, this is what we're going to do. This says the integral from -2 to 1 of 2x dx. Now, according to our definition, we want the limit as the norm approaches 0 of the sum as I goes from 1 to n of f of c sub I times delta x sub I. Now we're going to form some or make some restrictions here to designate the c sub I and the delta x sub I, and we'll do that in just a moment. But let's understand that it's equivalent. This is the same thing as saying since the norm approaching 0 means the same thing as n approaching infinity, we can say it this way. And we're going to, instead of using a sort of a variable width of rectangles, we're going to designate the delta x value here to be a fixed value just for computational purposes. And we're defining that delta x, the width of the rectangles, or the length of the intervals if you'd like, or length of subintervals if you'd like, as b minus a over n. And the b value is the 1, and I get that from up here. And then minus the a value is negative 2. So this total distance, you see, is 3, and 3 over n then is the width of each subinterval. All right, the c subscript I we're going to designate as negative 2, the left end, you see, of our interval, plus 3 over n times our counting mechanism. Now, let's understand what this means and how this counts and where that c sub I value is going to fall for each interval. And I think we've alluded to this before, but I want to make sure we understand it. Now, if we are talking about an interval here that goes from the left side of the y-axis to the right side of the y-axis, but I can illustrate this better by using a function and an integral that is to the right. And so I'll do that here. We're thinking then we have a function and its graph. And let's just say for our purposes here that this is where A falls. And this is where B falls. And we're looking to make rectangles here. And I'm going to make the rectangles fairly large. We're looking for rectangles that may be something like this. Now, we want to try to designate a c subscript I, and the I for this interval is 1, and for this interval it would be 2. The I is counting the interval. All right, and so for an I of 1, we want a c value that falls in here. An easy way to designate it is like this, is to take this A and then add something to it to put us in this interval. Now, we could just use A if we want to, but a convenient way to do it is to say, gee, if all of these are the same width, then just add the width of all of them, which in our case is 3 over n, you see, and then attach the counting mechanism to this width. And so when you attach the counting mechanism to it, if I is 1, then this is A plus 3 over n, and that's the point right there at the shoulder of that rectangle. And then when I is 2, you see A plus 3 over n times 2 puts us right here. And every time we count another I, all we're doing is shifting over this same width. One more time, we're counting another 3 over n width to add to that A value. So, okay, that's the idea of using as c sub I the left end point of our overall interval plus the width of our rectangles times the counting mechanism. Okay, now we have this. If this is c sub I, then f of c sub I means in the f function replace the x with c sub I. So we're going to replace the x in the 2x function definition. We're going to replace the x with this. So it's 2 times the c sub I, then times our delta x, which we said was 3 over n. And now it's a matter of cleaning up and doing a lot of manipulation. Now notice, and I hope you'll forgive me for not putting the I equals 1 to n on the summation indicator here, but we understand that that just follows down through our problem. Let's see, I'm multiplying 2 within this binomial, and I'm taking my time here with this, and I'm trying to illustrate how you might illustrate this on your paper. There's a tendency to try to skip steps here, and I want you to avoid that tendency. We have 2 times negative 2 is negative 4. 2 times 3 over n times I. The 3i can be thought of as the numerator here. 2 times the 3i is 6i, and that's over n. So now we're multiplying by 3 over n. Let's come up over here and continue. When we multiply 3 over n times that binomial, we get negative 12 over n plus 18i over n squared. And And then we can sort of distribute the idea of summation through this binomial. So it's the sum of that plus the sum of this. And so we have, let's see, the sum of this, then plus, when we talk about the sum of this rascal, we can think of the coefficient of I here as being 18 over n squared. And that's real helpful because that 18 over n squared moves to the outside of the summation notation, and we have the I following the summation notation. And that's important because we have a substitution for the sum of I. And that substitution is made here. It is n times n plus 1 over 2. And I'm kind of moving backwards here a little bit, but it's 18 over n squared times that amount. We'll get to that in a minute. Let's backtrack over here. The sum of a constant is simply that constant times the upper limit of the summation. So it's this times n. And now these n's cancel and we have negative 12. And over here, this is going to be, let's see, 18n times n plus 1 is 18n squared plus 18n. 2 times n squared, 2n squared. And now the 2n squared divides both parts of this numerator. And so we have the 9 plus 9 over n. And now the limit as n approaches infinity causes this term to go out. And we have negative 12 plus 9 or negative 3 for that integral. Now, notice that this integral is a negative number in this case. And now you can think of the idea here, you know, we think about area under a curve between a graph, the x-axis, and within an interval. And we talk about that under the circumstance that the graph falls above the x-axis throughout our interval that we're talking about, and it's real convenient to do that. However, you can illustrate the situation with areas that fall below the x-axis if you want to, and you can think about those areas as being negative if you want to, you know, just for imagination purposes and to sort of have a graphical image of this manipulation. You'll be delighted to know that we can calculate definite integrals by using methods other than finding the limit of a sum. And one of those methods is this. Suppose we have a situation where we want to calculate the integral from 0 to 5 of 5 minus x dx. Now, when we construct the graph of 5 minus x in the interval from 0 to 5, that graph looks like this. So we're looking for the area between this graph and the x-axis and within this interval from 0 to 5. And it's giving us a pattern that we're rather familiar with. It's the pattern of a triangle. So we can find the integral by just finding the area of the triangle. So the integral is equal to the area of the triangle. The area of the triangle is calculated as 1/2 base times height, 1/2 5 times 5, that's 12.5. So the integral is 12.5. Now, I said that there were a couple of things that you'd be delighted with, or a couple of situations where we could calculate the integral without having to go through the limit sum definition. And this is one of those cases. The other we'll encounter in the next section. I'm going to show you a very easy and efficient way to calculate a definite integral. Well, let's look at a couple of definitions now and a few properties that will help us in the manipulative process of integration here involving definite integrals. The integral from a to a, same number, of f of x dx is equal to 0. And it's pretty easy to imagine this in terms of a graphical interpretation where we want the area under this curve that is in an interval that is sort of non-existent. It's smashed into nothingness, you see. And when we're talking about the area from a point to itself, gee, there's no area there to calculate. So it turns out to be 0, and it's kind of an intuitive idea. The integral from b to a of f of x dx is the negative of the integral from a to b of f of x dx. So these are sort of opposites of one another. When we change these two, you see these two values, these are just opposites of one another numerically. Now, it's easy to see one application of this by applying the idea to our previous problem. That is, the integral from 5 to 0 of 5 minus x dx. G, this is the lower limit of integration, and that's the upper limit of integration, and generally we'd like to see this as a smaller number. Well, we can swap the two numbers if we just apply a minus sign. So it's the negative of, now swap these two, the negative of the integral from 0 to 5 of 5 minus x dx. And we found this to be 12.5, so negative 12.5 would be this integral. Here are some properties that will help us as well. The integral from a to b of f of x dx is equal to the sum of two integrals involving a point C. Now, think first about a point C that is between A and B. And by the way, we're assuming here that the situation, we can find the function is integrable within all of these intervals that we're talking about. All right, let's make that assumption. Imagine a point C that's between A and B. And think about this as an area now. And this area is equal to the area involving a point C from A to C plus the area from C to B. You see, that's the sum of these two areas. Now let me show you graphically what I mean. Let's move back over here, and I want to draw a diagram of this to make sure we understand geometrically what this looks like. If we had, okay, here's our function, and let's say this is the point A, and here's the point B, then we could identify a point C that's, let's say right here. And if C is in this position, then we could think about this area, all of this, is this area plus that area. So the integral of the function from A to B is equal to the integral of the same function from A to C plus the integral from C to B. And that is what this is saying. And that's basically what this is saying, A to C, C to B. Okay, but the restriction that C has to be between A and B is unnecessary. It's really easy to see in terms of areas, but it's not too difficult to see in terms of areas the other way. Let me show you what I mean. Suppose I put C out here. Now I'm talking about this area is equal to, all right, is equal to this area plus the negative of that area. Now I say the negative of this area because when we talk about the integral from C to B, you see lower limit, upper limit, lower limit, upper limit, these are not in the right order, you see. So it turns out to be the negative of the integral from B to C. And that's why I'm saying that we would have that this area is equal to this area minus that area. You see, that's what happens when the C is kind of outside of the interval between A and B. Okay. Here are two other situations that come directly from the idea of summation. The integral of a constant times the function dx means that we can take the constant and sort of write it outside of the integral notation. So it's the constant times the integral of f of x dx. And the other one is the integral of f of x plus or minus g of x dx is, and we can kind of distribute the idea of integration, so it's the integral of f of x dx plus or minus the integral of g of x dx. Here's a problem. I'm going to show you the parts of a problem, and then we're going to kind of put the parts together and illustrate how some of these properties or definitions can work for us. The first one is this. Consider the integral from 1 to 3 of x squared dx. Now, x squared, the graph of x squared is a curve, and when we start talking about the integral within an interval, then we're talking about the area under a curve or between the curve and the x-axis and within an interval. Okay, not a familiar figure. We can't use a formula like we could for finding the area of a triangle before. So we have to use the limit of a sum definition. So we have the limit as n approaches infinity of the sum as I runs from 1 to n of f of c sub I times delta x. And I encourage you to write this down every time you're going to use this definition. And notice that I have modified the definition a little bit. I'm not using as the norm approaches 0, I'm using n approaching infinity here. We're a little more familiar with that, and the norm approaching 0 implies this anyway. Also, I'm not using the x sub I idea. I'm using delta x, like we are fixing the width of each subinterval, or we are fixing the width of our rectangles here. And that value is established as, the delta x is the b minus a over n, b being 3, a being 1. 3 minus 1, 2, 2 over n, 2 over n. All right, so we have delta x is 2 over n. Now, f of c sub I, we have to establish c sub I. Now, once we do this a few times, it's going to become rather routine. But remember, the c sub I, a horizontal distance that falls within the ith interval, can be easily calculated by taking the left endpoint of our overall interval and adding the value of delta x, and then attaching a counting mechanism to it. That's all there is to it. So it's the left endpoint is the 1, then plus the delta x is 2 over n times the counting mechanism. And that sort of puts us on the right shoulder, the lower right shoulder of each of our rectangles. Okay, so we have, let's see, f of c sub I, here's c sub I, f of c sub I means the c sub I squared, because we're talking x squared here for our function. So this is squared, and when we expand and multiply by 2 over n, we get these fractions, and then we would distribute this summation idea throughout the fractions, and for this one, it's the sum of this constant, and for this one, we would extract the 8 over n squared because we want the sum of I, because we have a substitution for it in the next step. And here we're taking out the 8 over n cubed and multiplying times the sum of I squared. And again, we have a substitution for it. Well, I'm not showing the substitution for the sum of I and the sum of I squared. We've done it enough times before where you know this is going to be a mess for a couple of steps, and we simplify as well as we can, and it'll turn out that we have the limit as n approaches infinity of all of this. Now, we also know that for all of these fractions that contain n or n squared, those fractions disappear. They go to 0. So this goes to 0, that goes to 0, this goes to 0, and so we have 2 plus 4 plus 8 over 3, and it turns out to be 8 2/3. Okay, that's part of what I want to show you. Consider this integral. The integral from 1 to 3, now notice we're talking 1 to 3 again. The previous one was also 1 to 3, of x dx. Now, this integral, the function f of x equals x, is this within the interval from 1 to 3. So we're talking about the area that's under that graph, or between the graph and the x-axis, and within this interval from 1 to 3. So we're talking about this, the area of this figure. Now that figure is a trapezoid. And generally, when we deal with trapezoids, the upper and lower bases are parallel. So we would have to sort of lean it on its side in order to be able to imagine these being upper and lower bases. But at any rate, the formula is 1/2 the sum of the upper and lower bases. All this is averaging the length of the upper and lower bases, by the way, and then multiplying times the height. Well, let's see. Upper and lower bases would be this. Let's call this the lower base. If we think about cocking it over like this, then this would be 3, and that's 1, so that's 3 plus 1 in here. I've got it over here, the 1/2 of 3 plus 1, and then the height turns out to be 2. So that turns out to be 4. Okay. Now, what I'm trying to do here is show a couple of familiar figures and how quickly you can deal with integration, definite integration, when you're talking about functions that are of low degree. That is, first degree functions are really easy to deal with, and constant functions are easy to deal with too. Let me show you one here. Here we have the integral from 1 to 3 of 3 dx. Now, f of x is 3. So that's a constant function, a horizontal line that is at this y level. So y is 3 for every value in the interval. So we're talking about from 1 to 3. So here's the graph within that interval. And so we want the area of this rectangle. So it's simply length times width. And if we call this the length, it doesn't really make any difference. We could call it base times height. We could call it length times width. I don't really care. We're multiplying the two dimensions times one another. 3 times 2 turns out to be 6. All right, now, let's put all three ideas together into one seemingly humongous problem like this. Let's move back over here. I don't really have enough room on the board going over to the right. This board has an end. So I'll come back this way. Now, think about the integral from 1 to 3 of, let's say, negative x squared plus 4x minus 3 dx. Now, think about the work that we've done over there. You see, we can distribute this definite integral idea through our function here, through the terms of the function. So I could think of it like this. I could think of this as the integral from 1 to 3 of negative x squared, you see, dx. And then plus the integral from 1 to 3 of 4x dx. And then the integral from 1 to 3 of the negative 3 dx. Now I can simplify each of these a little bit. The negative, you see, that's a constant coefficient, and I can just take this outside like this. And then for this one, it's the same idea. I can write this as 4 times the integral of x dx, and we just found x over here, so that'll be easy. And on this one, it's the idea that we had here before, that this is negative, the integral from 1 to 3 of 3 dx. Now let's make some substitutions. Let's see, we have negative, the integral from 1 to 3 of x squared dx, we figure that over here to be 8 2/3. And then plus 4 times, let's see, the integral from 1 to 3 of x, over there, let's see, I'm looking over there, oh, it was 4. And then minus the integral from 1 to 3 of 3 was 6. And now all we need to do is clean up a little bit. 16 minus 6, this is 10. So this is 10 minus 8 2/3. Gee, that's 1 1/3. So we can put all of these ideas together right quick in a situation like this. And if you're faced with a situation like this before you've done that kind of work, which is usually the case, then you would want to separate the integral like this into parts, and then consider the various parts and pull out in all possible places. You want to pull out your coefficients like here, and then just deal with your definite integration right here. Now when you're talking about a constant, it's a little bit easier to deal with it as a positive value than a negative value, so you would snag out the negative sign. And if this is just a 1, then fine, you're thinking about it the same way we did just a little bit ago. And let's see if there's anything else I need to tell you about. Yeah, we just pull this negative sign out here. Pulling out those negative signs is very helpful because it allows us to deal with a positive integration idea that's associated with area. So it makes the problem pretty easy. Suppose we're given that the integral from 0 to 3 of some function is 4, and the integral from 3 to 6 of the same function is -1. Let's make some calculations. First, let's calculate the integral from 0 to 6 of this function. Well, we know from one of our properties that the integral from 0 to 6 is equal to the integral from 0 to 3 plus the integral from 3 to 6. And since this is 4 and this is -1, turns out the integral from 0 to 6 is 3. Suppose we want to calculate the integral from 6 to 3 of that same function. Now, we're given the integral from 3 to 6, but we want to calculate from 6 to 3. Well, we understand that this is the negative of the integral from 3 to 6. And so it is the negative of, let's see, from 3 to 6 was -1, and so this turns out to be 1. The integral from 3 to 3 of f of x dx. Gee, we don't need the values we were given over here, because when these two numbers are the same, we're talking about 0 for the result. Now, the integral from 3 to 6 of -5 f of x dx means that we can take this, this constant coefficient and we can stick it outside of the integral notation. And from 3 to 6 of f of x dx was given as -1. So this is -5 times -1, or 5 as the integral.